Welcome to the ADF Insider Essentials channel for another relaxing swim in the application module pool. My name is Chris Muir, I'm a product manager for Oracle Corporation. This is a second in a series of videos to explore the application module pool in ADF Business Components. In today's episode, we'll be dipping our toes into the basic AM pool settings, what they do and how this influences the scalability of ADF applications. Before considering the basic settings of the application module pool, we need to make sure that the entire audience has an understanding of some of the basic application module concepts, as this will set the scene for the rest of the episode. In defining application modules, as you know, you can define them as root application modules, nested application modules or AMs, or shared AMs. Now, at runtime, assuming the user has accessed a page with an ADF-BC data binding, a root application module instance will be created for the user session, and overall, as we know, these are stored in the application module pool. As we also know, only the root application module is responsible for the transaction, connection, and state management. A nested application module is simply a design time concept for grouping view objects. They themselves nest under a root AM, and they delegate all the transaction, connection, and state management to their root application module. So for all intents and purposes, we can ignore nested application modules from the following discussion on application module pools. You just equate any nested AM to its parent root AM. Finally, we also have shared application modules that are designed to share state across user sessions, ideal for data like postal or zip codes. A shared application module maintains its own application module pool, but with a maximum size of 1. So again, we'll ignore the shared application module, and overall we're going to focus on root application modules for this ADF Insider Essentials series. So let's hereafter focus on root application modules and see where the application module pool settings are defined to store these. In JDeveloper 12.1.2, if you locate and open your application module in the model project, select the Configurations tab, you will see two entries, App Module Local and App Module Shared. ADF for the AM pool settings allows named configuration sets, such that you can use different combinations of settings for different reasons. The typical example for that is we see here via the two configuration sets that exist. In fact, JDeveloper created these by default. App Module Local is the default AM pool settings for a normal root AM. App Module Shared is the default AM pool settings for a shared AM. Note that these settings are stored in the bc4j.xconfig file of your model project. As we're going to focus on the normal root AMs and not shared AMs, we'll continue with the App Module Local configuration set from here on in. As we know, root application modules are responsible for connecting to the database, and the underlying entity objects and view objects use the connection to perform DML queries and transactions against the database. Typically, when we create our first set of business components via the business components from Table Wizard, we define our application's connection. Those settings beyond the wizard expose themselves here against the application module in the Edit Configurations dialog. You have two choices for defining the connection, that of a JDBC URL or JDBC data source. Oracle recommends the JDBC data source over the JDBC URLs, and what this essentially means is when the application is deployed to the WebLogic server, a WebLogic server database connection pool will be used over an ADF maintained connection pool at runtime. Now let's be clear here. We're talking about a connection pool, not the application module pool. These are entirely two separate concepts, two separate caches. One is a cache of connections and the other is a cache of application modules. It just happens that the application modules need connections to connect to the database. So the application modules need to know where they're getting those connections from. And that can be either from an ADF-BC managed connection pool or the recommended managed WebLogic server connection pool using JDBC data sources. A question arises, why do we want to use the WebLogic Server Managed Connection Pool over an ADF-BC Managed Connection Pool? As the WebLogic Server Database Connection Pool can be maintained by the WebLogic Server Administrator independently of the application doesn't need to be redeployed if the connection details need to change. Multiple applications can share the pool and so on, so this makes the WebLogic Server Managed Connection Pool a better option. Now we'll move on to the Pooling and Scalability tab. Assuming from the previous tab you do choose the JDBC data source, you'll notice that the right-hand side of the Pooling and Scalability tab, that is the connection pool options, are greyed out. The reason being, these were the options for configuring the ADF-BC Managed Connection Pool. But as we've chosen to go with a WebLogic Server Connection Pool instead, there's nothing to configure on the right-hand side. Those settings will be ignored. Alright, now that we've the database connection settings out of the way for the application modules, we'll now discuss the application module pool settings themselves. Now the first question arises, why do we have settings for the application module pool in the first place? Isn't there a one-size-fits-all set of settings for all the ADF applications out there? As the application module pool is inherently related to serving the number of application users, and by inference these have different scalability and performance needs, each ADF application has a different set of requirements of the application module pool. For some applications with few users, we take advantage of loading as many application modules into memory as possible to improve the user throughput. Alternatively, for an application that may have a huge amount of users, loading all the application modules into memory will inherently hit the limits of our physical memory, so that would be undesirable. Therefore, no one application is the same in terms of its application module pool requirements. And thus, having a one-size-fits-all application module pool wouldn't work. We need to be able to configure the application module pool, its size, its operations, to tune it for our application's particular characteristics. So let's investigate those AM pool settings in more detail now. In focusing on the left-hand side, we can see a number of settings under the application module pooling heading, and it's these settings we're interested in discussing further. The first option we best cover on discussing the application module pool settings is the one labelled Enable Application Module Pooling, also known as jbo.ampool.doampooling. It's this option, which is turned on by default, that turns on or off the whole application module pooling mechanism. Obviously, if you want to make use of the AM pooling options, you leave this on. In fact, if the Enable Application Module Pooling option is off in a production system, Oracle will not support your application, so it must be on. But there is a limited use case where we do turn this off, and we'll cover this or discuss this in a later episode in the Best Practices episodes of this ADF Insider Essentials series. Before we move on, do you notice how I referred to the option as Enable Application Module Pooling? But I also said it's called the jbo.ampool.doampooling option. Why did I do that? Basically, all the options that I'm describing on this page, the labels you will see are for your convenience to make it easy to understand what the option does. However, each option is represented by a key and a value, much like jbo.ampool.doampooling. So, if we return to the Pooling and Scalability tab, all the options you see on the left-hand side, here's the relating key name. Now, admittedly, pretty much most of the keys are as meaningful as the label, but there are some exceptions we will cover later where the keys and the label, well, can be a little bit confusing. So we'll go into those in detail to make sure that you don't get confused. As you can see, it does appear to be an overwhelming set of settings. And indeed, there are some options hiding in the Properties tab that are not even shown here that are as important as the others, such as jbo.ampool.timetolive and jbo.ampool.disconnect_level. Now, some people who have investigated AM pooling get really overwhelmed by all these parameters. Without a doubt, these can be hard to learn. But why? So Miller's law says the average human can only hold 7 objects in memory at once. there's 12 application module parameters. No wonder so many people find it hard to learn the AM pooling options. But my job here is not to overwhelm you, but rather initially explain the basic options and how they work. The trick to doing this is not introducing all the options at once and explaining how they interact, but rather introducing them one by one and explaining why they exist one by one, what problems they try to solve one by one. It also helps in doing so to categorize the parameters by their purpose, and this will give you a better idea of which parameters relate to each other. Broadly speaking, the pool parameters can be broken into 4 categories. Firstly, those that control the pool size, that is, how small or large the pool can be. Next, performance, or in other words, those parameters that control the scalability and throughput for users. The third category, how many AMs in the pool are cleaned up, including what happens if the user times out or logs out. And finally, the fourth category of AM parameters aren't so much about the AM pool, but rather settings that control how the individual application modules behave. Now, as we said, there's a lot of parameters, but let's start with these first two that control the pool size, that is the initial and maximum pool size. If we return to the AM pool settings, you can see both these parameters defined at the top. The initial pool size maps to the jbo.ampool.initPoolSize parameter and the jbo.ampool.maxPoolSize parameter for the maximum pool size. Let's consider the jbo.ampool.initPoolSize parameter first. The minimum AMs the pool can have in it when starting is 0. Eventually we'll instantiate and start using application modules, but again the pool does start from 0. Now obviously the act of populating application modules will have an inherent cost, but it's also the act of instantiating the AMs will do too. The jbo.ampool.initPoolSize parameters, or more commonly referred to as the initial pool size, is designed to solve this problem by priming the AM instances before they're needed. When the AM application comes up, we can ask the pool to pre-initialize a number of AMs by setting this parameter above the default value of 0. As such, assuming there's still initialized AMs available when a new request for a new session arrives, the request won't have to wait for the AM to be instantiated by the ADF application module pool. To be clear, this won't remove all the startup cost. The AMs aren't preloaded with data via the entity objects and view objects. We're just initializing the parent AM. So this is a very small benefit, but not a huge speed gain. Note the jbo.ampool.initPoolSize does not control the minimum number of AMs available in the pool. If you set this setting to say 5, if those AMs are never used in a certain period, the ADF AM pool monitor will clean up the AMs. We will discuss the monitor more in another episode when we consider the AM pool cleanup parameters. Separately, the jbo.ampool.maxPoolSize controls the maximum number of AM instances created, the default being 4096. As we would expect, exceeding this number of AMs would result in an error, essentially putting a cap on the AMs and the total memory the app will consume. Now, as we're about to learn, the maximum pool size is rarely, if at all, hit, so we tend to leave it as a default value, and this is due to the parameter called jbo.recycleThreshold. The jbo.recycleThreshold parameter is very special to how the ADF-BC application module pool works, and how we tune the application for either user throughput or scalability. Now, to understand the recycled threshold parameter, we need to go back to some concepts we mentioned in the previous episode. You might remember that we mentioned the concepts of passivation and activation of application module states. We described a scenario where we can store the state of 400 users in memory, but when the 401st user comes along, we passivate the state. That is, store the state for an existing used application module in the pool into the database. and then we clear the AM for the incoming 401st user. Later, if the original 400th user, that is the original AM user, comes along and makes a request, we passivate the state of another AM to the database, doesn't matter which one. Then we activate the state, that is the 400th AM, from the database and rebuild the 400th AM state in the pool for the original 400th user. Now, I'm betting some viewers are feeling a little out of their depth on this description. So let's describe all of this diagrammatically so hopefully you can tread water. So, diagrammatically, here's our application module pool, which, for the purposes of simplicity, the minimum and initial AMs instantiated is 0. And the maximum AM set by JBO AM pool max pool size equals 400. By default, this is normally 4096, but again, for purposes of simplicity, let's make this number smaller and by definition easier to describe in the theoretical description we're about to embark upon. So, at minimum, the pool can contain 0 instantiated AMs all the way up to 400. And all the way back to 0, depending on the number of active sessions requiring AMs. So at minimum, the pool can contain 0 instantiated AMs all the way up to 400, and all the way back to 0, depending on the number of active sessions requiring application modules at this time. Now imagine our very first request for our very first session hits our application and requires an application module from the AM pool. The AM pool in this case will need to instantiate an AM. Let's call it AM number 1. Then make it available to session number 1 to fulfill its request. Now there's a gross simplification of the JSF and ADF lifecycles here, but to say the ADF and JSF servlet uses the AM for that session to do a whole bunch of work. As we're not interested in the whole lifecycle for this video, we'll keep what happens in the response after the AM is fetched to this simple example. Once the response is set, application module 1, which is allocated to session number 1 with its associated state, will sit idle in the pool. If session number 1 comes back with another request, the AM pool will give it exactly the same AM number 1 as it carries all the state for session number 1. How it does this coordination, well, there's an internal mechanism and we don't want to go into that because it reveals too much complex detail for now. Just to say that ADF-BC is smart enough to coordinate the sessions and AMs. In doing so, the AM is considered checked out of the pool, though it never actually leaves the pool, and its status is unavailable while the thread servicing the request does its work. Again, eventually an AM response will be formed and sent back through the JSF and ADF lifecycles to the browser or the client that requested it. And AM number 1 for the first session will go back to being idle. Over time, other sessions, here session 2, separate to the previous session number 1, will also want their own AMs to work with. Here's session number 3, here's session number 4, right up to session 399 can all be allocated their own AMs, their own state, and so on. Now eventually we'll get our 400th user or session requesting their own application module. And at this point, our AM pool is essentially full. Now meanwhile, the previous sessions may still be coming in with new requests. Here we can see session 209 and the AM pool gives it AM 209 to work with. Here's session number 4. Here's session number 116. The point being the AM pool is maintaining the original AM and its state for that user session over multiple requests, solving the HTTP statelessness issue we described in the previous episode. So what happens if the pool is still full? It's actively engaged servicing the maximum of 400 sessions and we receive a request from the 401st session. Do we just reject the session saying, sorry, we're full? That seems to be a bit pointless, where the other 400 sessions are completely idle, and in computing terms have been idle for quite a long time. Is there anything we can do to solve this problem? ADFBC and the AM pool includes the concept of passivating and activating state to a passivation store, as we mentioned earlier. So as we can see here, we're taking AM number 400 for session 400 and we're passivating its state. That state is then stored in something like an Oracle database. Indeed, ADFBC writes this state to a table called PS_TXN in an XML format. And essentially the state of the AM is contained within a row of the PS_TXN table to be reused later. Once the state of the 400th AM is passivated, the actual AM itself can be reset and made available for a different session to make use of, in this case the 401st session. Thus, the 401st session and its request and response can then be processed even though we hit the pool limit. Now, meanwhile, other session and requests are still coming and going. Here we have 209, 4, 116, but eventually session 400 will return. Now this causes us a problem, as the 400th AM has been reset and being used by the 401st session. Effectively the state of the 400th session has potentially been lost. What does the AM pool do in this case? Just like previous, we now passivate the state of AM number 400 to the PS_TXN database table. We then reset the 400th AM to flush its data and AM settings, which were specifically for the 401st session. And then we activate or read the original state of session 400 AM from the database PS_TXN table, rebuilding the AM to the state the 400 session request requires before it was passivated previously. This allows the system to respond to the 400 session request as if the state had been maintained over multiple requests without the session knowing any different. Yet this does exhibit a bit of a limitation in the system. What we discovered over the life of the AM pool and all the session requests coming in was that only around a quarter of the sessions were effectively active in this particular application example. That is, all the sessions are valid and all legitimate sessions, but we found that nearly 3/4 of the sessions were idling. Is there some way we can take advantage of all these idling application module instances in the pool, possibly to reduce the overall memory footprint of the application? The application module pool does this by introducing a feature known as the referent pool size or JBO.recycle threshold that we mentioned earlier. What this parameter does is it defines the pools into a set of logical active and inactive application modules. That is a set of AMs that we are pinning to the pool as we consider them to be more active, and we want to provide them better throughput by holding them in memory in the pool. These AMs are said to have session affinity and are referenced or pinned by a specific session. Not only do these AMs receive better throughput by holding them in memory, but as they aren't involved in a passivation activation cycle, they avoid the I/O overhead associated with this. And they can even take advantage of other features like reusing a database connection from the connection pool, reusing the JDBC prepared statement cache for the connection, and so on. So if the user had a preference, they'd want their AM associated with their session to be a referenced AM, as the throughput for that user will always be faster. Vice versa, the AMs that have been returned to the pool after processing, if it's found the number of referenced AMs in the pool exceeds the threshold, then the AM is actively passivated, making the AM reusable by another session, giving us scalability. To make this easier to understand, let's again consider this diagrammatically. So we pretty much have the same setup as before, 400 AMs in the pool and the database PX TXN table to passivate to. For purposes of describing the discussion, we'll introduce a JBO recycle threshold of 200. Now, like previous various sessions and requests will come in. We'll serve these with various dedicated AMs like last time, right up to the number 200. As previous, earlier sessions make more requests and will receive the same application module. Eventually, when the AMs is up to 200, equal to our recycle threshold, we will hit our 201st session request. In this case, the AM pool identifies the least recently used AM in the pool. For purposes of the demonstration, let's say that's AM number 16. AM number 16 state is then passivated to the database's PSTXN table. And then session 201st uses the newly reset 16 AM to service its request and form its response. Meanwhile, more original sessions are still being served from the pool, and now a brand new 202nd session is received. We identify the 46th AM as the next least recently used AM in the pool. We passivate its state to the database, reset the 46th AM in the pool. Then the 202nd request makes use of the now free 46 AM to service the response to the 202nd session. So at this point, though the pool is constrained to service 200 AMs under the recycle threshold, we're servicing 202 sessions. 200 most active sessions and their AMs are kept in memory. And we push the least most recently used AMs off to the persistent store, where we can activate them when their associated session returns. In addition, we save significant amount of memory by pushing inactive sessions off our WebLogic server Java heap. So theoretically, with the combination of the AM pool and the passivation store, we have an unlimited amount of user sessions we can satisfy. Now again, this is a gross simplification for the discussion here for learning purposes, but it gives you an idea of the overall intent of the application module pool, the recycle threshold, and how the passivation store is used. Great, so we have a mechanism that will optimize the throughput for our most active users, or a mechanism that allows us to scale right out the number of users we can service. But this does leave us asking a few interesting questions. What state is actually passivated and activated from the database on behalf of the application module? And if we're always passivating when we hit the recycle threshold, why do we have a parameter like jbo.ampool.maxPoolSize? We'll never hit it. These are all very good questions. And guess what? These are questions we'll answer in our next our next episode on the ADF-BC application module pooling episodes. Cheerio!